Vectors and calculus. So you all are aware, clearly, of what a vector, full screen this, a vector is. So, you know, let's just, basically it's an arrow. And usually in a given coordinate system, usually we choose Cartesian coordinates, don't we? A vector has components in the x direction with unit vector notation I, a component in the j direction, the y direction, unit vector j, and a component in the k direction. So if you've not seen that notation before, don't worry. All I'm really saying is that a vector v can be expressed as three components, one in x, one in y, and one in z. So we're all happy with that, hopefully. Next, let me just check the waiting room. Okay, so calculus, you've met the derivative. So you are, the first time you come across it, you consider dy by dx, and the second derivative, d2y by dx squared, to tell us the rate of change of a quantity and the rate of change of that rate of change. And you could carry on, of course. So calculus is to do with the analysis of change. In fact, that's a good way of thinking about calculus, the analysis of change. So the question then is, what happens when we want to put the two together? Because in physics, we deal with vectors all the time. Okay, we live in a three-dimensional, in terms of space, three-dimensional universe. Hopefully this Wi-Fi connection holds up. And everything like forces, electric field strength, they're all vector quantities. So we need to put these two together. And I'd like to introduce you to a symbol, this symbol. So this is called del or nabla. You'll see sometimes. I've never used that one, to be honest, but you'll see it. This is the one, del. It's like an upside down delta, isn't it? This is a vector operator, and it's basically this vector. Like that. It's like, so it's a vector gradient operator. So it's the three-dimensional generalization of a derivative. So that's fairly straightforward. Okay, instead of writing that whole bracket or the whole vector, we just write an upside down triangle. Now you can do various things with this del operator. So there are three things you can do. You can do this. You can find the gradient of a scalar. So you can say you've got a scalar, let's call it S for scalar. This is called the gradient or grad of S. And that is a vector which ends up being ds dx, ds dy, and ds dz. So it's just basically how is S changing in each direction separately. So that's the gradient. The next thing you can do is called the divergence, which involves something called a scalar product. So it's basically a way of multiplying vectors together. So if you find the scalar product of the gradient operator, so del, and a vector v, that gives you something called the divergence, or div, of v. So it's the divergence of a vector, and that, and again, first years you'll do scalar products in maths, but if you take the scalar product of these two vectors, you get the following: dvx by dx plus dvy by dy plus dvz by dz, because the scalar product is you basically take the product of the x components, add them to the product of the y components of the vectors, then add the products of the z components of the vectors. So this actually gives you a number, a scalar, doesn't it? It's just a number. So hence the name scalar product, okay, because it's two vectors multiplied together to give you a scalar. Final variation is called a curl, and that is something called a vector product. So this is the curl of V. And this time, I'm not, should I write this out? The second years might understand this. So to find the curl, you take the cross product, or the vector product, which is basically, now, what's the best way of me doing this? You can go and look this up. You find the determinant of this matrix. D, Vx, Vy, Vz, I, J, K. So finding the determinant of that matrix gives you the vector product. Anyway, it's a vector. So you end up getting a vector with a load of terms. Okay, so I'll write the first term just to show you the idea of what it looks like. So it's a sort of combination of the dx, dy's and the vx's and the vy's. So the first one would be dvz by dy minus dvy by dz. And then the other terms look similar. Anyway, what's important is that gives you a vector. So in vector calculus, which is what this is called, so this whole sort of new area is called vector calculus. You do it in the first year of university engineering or physics. There are three types of derivative. Well, are they derivative? I suppose they're sort of derivatives. There are three variations of derivative. There's the gradient, the divergence, and the curl. So gradient, I'll tell you what each of them mean now. The gradient is basically the slope as it is normally. So if you have a function, let's say, let me draw a field. So say I have a field, which is by a load of arrows in space. Then the gradient tells you something about how the value of the vector changes. Why is this not appear? Oh, hang on a minute. There we go. It tells you something about how the value of the vector changes as you move through space in any particular direction. So it's literally just the same old gradient we're used to. It's just in a particular direction. The divergence, so this thing, is a measure of, I'm going to write this over here. The divergence basically tells you something about the flux, the net, the net flux of a vector field. If I can spell, I'll try and explain what this means. Net flux of a vector field, and it's actually per unit volume through a closed surface. We'll come back to that. So it's basically to do with the flow of the arrows. So for instance, if I drew an orange box through in this set of arrows, there are as many arrows coming into this as going out. So the divergence of this field, if it's uniform, the divergence of this field will be zero because there are as many arrows going in as coming out. The divergence of this field, so second years who've done electric fields, right? If I've got a charge here, say, the divergence of the field of this through this spherical surface surrounding the charge is going to have a value, isn't it? Because there are arrows coming out. There's a net outflow of vector field of arrows, right? So this has a divergence, this field, because there's a source of field lines in the middle of bound by the surface, and there's an outflow. What's the curl? Well, again, more on the divergence later. The curl basically tells you something. Its name is quite good because it tells you something about the circulation or the vorticity of the field. So it's sort of a measure of the vorticity, the rotationality. That's not, I don't know if that's even a word. Vorticity is better. Vorticity of a field. In other words, This field has zero curl because there's no element of that field which is called kind of rotating or curling around a point, whereas this field does have a curl, right? Because there's a rotational aspect to it. So it's a vector which tells you something about the vorticity of a field. Now, I think some of you who've done fields before can already see how this might tie in with the description of fields: magnetic, electric, and gravitational. So that's the mathematical introduction. Now, bear in mind that I learned this at university and I've not taught it since. So it's been 13 years since I actually did this myself. So just bear with me. It's not going to be a comprehensive introduction. So these are Maxwell's equations. Certainly in a vacuum, right? They do change. There are additions when you have a medium present. So these are sort of in vacuo, I guess. I'm going to take them in turn and show you what physics lies within. Number one, I'm going to write them. I'm going to sort of label them 1, 2, 3, and 4. Now, whenever I introduce these equations, I always bang on about how you can basically derive all the laws of electromagnetism, light, optics even, from just these equations, right? It's like you can write a load of physical laws. I'm just checking the connection. A load of physical laws down on the back of a postage stamp. It's just so nice. So I love these equations, basically. So equation 1, I'm going to rewrite it down here. This is the divergence. Remember this dot. The divergence of E is equal to rho over epsilon naught. Rho is the charge density. So that's coulombs per meter cubed, I guess. Charge density, charge per unit volume. Now, remember what divergence means. Divergence is to do with the flow, the net outflow through a particular surface. So what this is telling me is that if I have a surface, the divergence of E through that surface, imagine that's a spherical shell, is equal to the charge density enclosed within that surface. So if there's no charge present, there's no divergence. You're not getting any net flow of E field out of that surface. Whereas if I put a charge here, and I'll put it in the middle for simplicity's sake, if I put a charge there, Q, that means that now this term is non-zero, which means now we have to have a divergence of net outflow of E field through that surface. And as we know, the field around a point charge looks like that, right? And if it's positive, the field lines do something like that. So in that sense, this equation sort of tells us about, so you can describe charge as acting as a source of E field, because you can almost think of it as producing flux lines, which then travel out of that surface, if you like. Okay, so that's what divergence means. In fact, if you can rewrite this equation, and you can go check a math textbook, you can rewrite this in an integral form, which is E dot ds, where ds is an element of this surface area, equals Q over epsilon naught. And of course, if the whole surface area is a sphere, then S is 4 pi r squared. So then you get the integral becomes E times 4 pi r squared equals Q over epsilon naught, which of course becomes E equals Q over 4 pi epsilon naught r squared. So that law is basically Coulomb's law. Okay, so equation 1 is you basically get Coulomb's law from that. The reason you meet the first Maxwell equation, right, you can deal with more complicated situations, right? So usually Coulomb's law as written only applies to spherically symmetric situation with a charge sort of distributed evenly, or enclosed within that surface. This allows you to deal with situations which are more complicated, obviously. This is called Gauss's law. And this is equally applicable to gravitational fields because you can replace the charge density by mass, can't you? And epsilon naught by another constant. For those of you who first years who don't know, this is just the permittivity of free space, which is a constant. 8.85 times 10 to the minus 12 farads per meter. Number 2, so that's equation 1, tick. Equation 2, oh, come on. It'll catch up with me, don't worry. I need to move closer to the, I'm in Brookcore Garden. Hang on. Okay, equation 2, oh God. Divergence of B, grad dot B. So the divergence of B is 0. Now, what that means is for a magnetic field, let's draw my spherical surface again. For any surface, you cannot have a net inflow or outflow of B arrows, of magnetic field vector arrows, right? So what that means is this is impossible. You cannot have a magnetic field which does this. That's got a name. This is called well, it's not called this, but the concept of no magnetic monopoles existing. You can't have an isolated north pole, which produces magnetic field, and you can't have an isolated south pole, which produces field lines, because you'd be able to draw a surface around the north pole and then get this situation. So this equation basically is the same thing as that. What can you have then? Well, through a surface, what this is telling you is that if I've got field lines coming into it, then they also have to leave as well. So you can't have a net inflow or outflow of lines. And if you look at any magnetic field, north, south, so like field around a bar magnet, say, if you look at any position, you will always find that that's true. So the field coming in will be the same as the total field going out. By the way, no alcohol, so it's non-alcoholic beer, so I'm allowed to do it. That's equation 2. No magnetic monopoles exist. Tick. Next. Equation 3. The curl of E is minus dB by dt. Now, I'm not going to go into too much about the curl. You could basically read this as E field is generated by a time varying B field. So whenever you have a change in the magnetic field, a changing flux across a region of space, particularly a conductor, you will get an EMF, an E field, and hence an EMF induced. So second years and first years, if you've done IGCSE or GCSE, this is induction. This is Faraday's law written in like properly. So this is Faraday's law. Remember, the EMF induced in a conductor is, or across the ends of a conductor, is directly proportional to the number of field lines cut per second, or the rate of change of flux linkage. That's this equation. Okay, so just because it has a this mathematical notation, gets away from the actual physics, right? What I want to focus on today is not the mathematical sort of symbology. I just want to talk to you about physics and what these mean. So this means Faraday's law. E field is generated by a time varying B field. And this tells you, of course, that means also the EMF is going to have some kind of, it's not just going to be linear or sort of, you know, uniform. It's going to have some kind of curl to it. Like it's going to be have some vorticity to it. Okay. But at heart, this equation just means E field is generated by time changing B field, right? That's change with B with respect to time. If the B field is not changing, you don't get an induced E field. So that's the meaning of equation 3. We're not doing too badly, are we? You know, you think these equations are so complicated, and then 3 of them you basically already have come across if you're second year. Number 4. Oh God, right. B fields. So I'll read this out as I'll read out the interpretation as I write it. B fields with vorticity are generated by currents. This is current density. So B fields are generated by electric currents. Okay, we know that one, don't we? And also by time varying electric fields. Okay, so if just as changing magnetic fields generate an electric field, changing electric fields generate a magnetic field. So there's a two-way process going on here, which is important for a minute. I'll come on to, for a reason I'm going to come on to in a minute. So this is called Ampere's law, this bit. Ampere with a grav. Ampere, I think. Anyway, let's just write it without an accent. I'm not sure. Ampere's law tells you that currents generate magnetic fields. And second years again, you see this equation for the field around a wire. Here's the mu naught current. And then the 2 pi r comes about because when you've got a curl, you can rewrite this as a line, what's called a line integral, b dot dl. So if you consider a line, a circular path of radius r around your wire, say this wire has a current in it flowing towards us. If we consider a line, radius r, it's got a circumference of 2 pi r. So we get b times 2 pi r equals mu naught j, current density. So you can see that then we get b is mu naught j over 2 pi r. So even that equation, which some of you have come across, comes from this directly. The other bit you've not come across probably, this bit is saying that, yeah, a time varying E field will generate a magnetic field. Now that's important because there are 2 interesting, I'm going to give you 2 consequences or follow-ons from looking at Maxwell's equations. Did I add that derivation? No, I didn't. So, consequence number 1. If a changing magnetic field generates an electric field and a changing electric field generates a B field, you can actually combine these equations. You can combine the equations to generate a wave equation. Now, I wish I had, let me just see if I've got it here. Somewhere I've got a document. In fact, I might insert it. Just give me 1 minute. So, and guess what? When you solve the wave equation, you find, let's see where I should have put it. I'm going to put this. Let's see if it syncs first. You generate electromagnetic waves. So from Maxwell's equations, by combining them in a clever way, you can, okay, it's appeared, that's fine. I'm going to add a document to show how you go from Maxwell's equations to electromagnetic waves. I hope the document is saved on my desktop, because it's worth you seeing. Just, it's going to appear if OneNote actually lets me insert the printout, which is, OneNote has this annoying habit of making me attempt it several times. So hopefully it's appeared now. Give it 1 minute. Look at this. Maxwell's equations there. Now you see they've found the curl over here with this determinant. Anyway, that's the detail. I'm not going to go through that. You generate this equation and that equation. Now they're wave equations, which you can, those of you who've done SHM, whenever you see a second derivative like this, you should be thinking to yourself, wave-like trigonometric sine/cosine based solutions. And of course you do, right? You get general solutions which are cosines or sines, depending on what boundary conditions you choose. And this constant here tells you what the speed, or it's related to the speed of the waves. So that's why the speed of light is written in terms of the permeability, mu naught, and permittivities of free space. So that's one interesting consequence of Maxwell's equations. You get electromagnetic fields. So Maxwell predicted the existence of them before Hertz first measured them or first detected radio waves. I think that's when they were first sort of observed. And then obviously we now know visible light is part of that spectrum. I'm almost done. This is a speed session today. Next interesting consequence. So I'll draw a big arrow down here. Number 2. Now this is, there are loads of interesting consequences, right? You can derive the whole of electromagnetism from them, but plasma is basically ionized gas. Ionized gas, it's a state of matter in its own right. It's the most abundant state of matter in the entire universe because stars are made out of it. Well, dark matter actually might be more, okay, let's not get there. So normal matter, right? Plasma is like a big part of the universe. Now, unlike in solids, liquids, and gases where you don't have any free charge carriers, in a plasma, say you've got plasma, there are loads of electrons, ions in that region, right? So when you have magnetic fields or electric fields interacting with the plasma, you can't just sort of, it's not so straightforward to deal with it, because all these charges in the plasma can move around and are affected by the field. The fact they can move is important, because things that can move, where you've got a thing that can move around and sort of have the atoms and the ions move around each other, that's called a fluid, right? Now, some of you, and this is something that engineers will be interested in, fluids are governed or described by something called Navier-Stokes, the Navier-Stokes equation, which is, you can go away and look that up. Maybe I'll do an extra session on that as well. But it's basically, basically using Newton's laws, like a classical description of fluids. But in order to describe plasmas, okay, this is the cool bit, or I think it is anyway. You have to take Maxwell's equations, right? Because obviously you've got magnetic fields generated by moving charge, right? So the charges which move in a plasma generate magnetic field, which then interacts with the other charges in the plasma. Okay, so you can see how magnetism and electromagnetism is going to be very much involved when you've got moving charges. So you need Maxwell's equations, but because it's a fluid, you also need Navier-Stokes. And if you add or combine the Navier-Stokes equations with Maxwell's equations, you actually, this is a completely separate topic within physics, which describes the dynamics of plasma. Okay, so this is required to describe stars in detail. It's called magnetohydrodynamics. Don't worry about the hydro bit, right? It's nothing to do with water. But this area of physics or science is the study of plasma and the interactions of magnetic fields with the plasma. So, you know, magnetohydrodynamics is a big part of astrophysics, the study of stars. Whew, right, I'm getting quite cold now. So that was more or less, I mean, I hope that you got something out of that. That was me trying to pick apart Maxwell's equations and show you that there's something in there that you already know, namely Gauss's law and Coulomb's law, the fact that you can't have magnetic monopoles, the fact that you can induce currents or induce voltages and hence currents with a changing magnetic field, induction, which is the basis of transformers, generation of electricity, and, you know, and then you've got creating magnetic fields with currents, changing electric fields, and all of that put together gives us electromagnetic waves, which have changed our lives immeasurably. Phone being an example. Right, that's it. So hopefully they're not as mysterious as they might have seemed previously. Those of you who love maths, you can go away and look. There'll be videos on YouTube describing what div, grad, and curl mean. But those are, that's my understanding of them. And yeah, that's it.